Hello, my name is Ralf Gerlich from the German software technology company BSSE. And together with the FZE Research Center for Information Technology and the University of Würzburg, we are investigating how to use non-conformant software, non-ECSS-conformant software, such as open source software and AI in critical applications. So what we want to do is we want to provide a process that enables us to use AI and non-ECSS conforming third-party software in applications that would otherwise be considered criticality category B or C according to the ECSS. And the driver behind that is IBUS. IBUS is a concept for a modular satellite, and we're physically talking modular, in the sense that we have building blocks that are also specified in their physical properties. There's little cubes, which on each side have a connector for power, thermal, structure, and network connectivity. And it's highly distributed computing that we're talking about. And for implementing applications there, we intend to use, for example, the robot operating system or AI networks that have to be implemented using open source technologies such as PyTorch or TensorFlow on the development side. Of course, the AI itself has its own challenges regarding verification and dependability. So one application is in-orbit assembly and maintenance. Given a possibly partially assembled satellite and a list of required features together with a set of cubes that we can add to the satellite, we have to figure out in which order to do that. That is normally a computationally expensive task, but AI can help us to improve the computational complexity here. Another aspect is that we want to perhaps change the configuration, the hardware configuration of the satellite in orbit or during mission. And that means that we have to adapt to change. We have a new plant when we change the hardware configuration of the satellite, and then we also need a new controller. Alternatively, you could think of adapting to change in dynamics due to fuel consumption or degradation and failure. In this context, we come across software packages that we intend to use, would like to use, that have not been developed according to the ECSS or any other applicable standard. We call this software non-conformant software because it does not conform to the applicable standards. One example is ROS, the Robot Operating System, which is currently in development in its second version, and which, for example, is considered by NASA for their Viper mission. The packages that we might need for our application here would sum up to about 1.3 million lines of code, both in C++, C, and some of it even Python. And the C++ is the real deal. So we're talking about templates and all the stuff that makes C++ a nightmare. It would be running based on Linux, so we're not talking about the ROS, the robot operating system itself only, but also about the operating system, which is virtually non-qualifiable anyway. We are also talking about development tools for machine learning, such as PyTorch or TensorFlow, which are used in the development cycle. Given that these are critical applications, the ECSS would require us to qualify them just as we would have to qualify software that would be in use on board. These packages are already widely used, have a large community of maintainers, and as well, they have been developed in Python, a language that is difficult to properly verify to the standards that we normally apply. So if it's such a hassle, why use non-compliant software at all? So the advantages of ROS2, for example, we have a huge set of pre-implemented robotics control algorithms. We can use ROS2 right now for development, for for research. But once we have to transform this into an actual application, we have to essentially redo it. And that doesn't seem useful. So we have a large community, including the automotive industry, which is more and more interested in using ROS2 in their actual application on the road. We have with ROS2, different from the first version, a development focused on dependability. There are actual process standards being established even in this agile open source development. And finally, parts of it, the main middleware, has been certified according to ISO 26262 with only minimal modifications. So that also speaks for the dependability of ROS2. The modified version of these basic elements of ROS are known as Apex OS and have been set up by a company named Apex AI, specifically for the use in the automotive area. So if we wanted to use ROS, well, we would have to qualify it or we would have to re-implement it. And just a basic estimate of what it would cost us to re-implement ROS to at least those parts that we need, with a considerable markdown of 25% of the code size, considering that probably we wouldn't have to re-implement everything of it, we would come around with an estimate of about 80 to 1,000 million euros. That's a huge range that is due to the insecurity in the estimate. However, a useful estimate is probably in the range between 100 and 300 million euros. That's a large number even for the space domain. So what would be the risks of just using the non-compliant software? Well, the risks would apply to the RAMS properties of the system: reliability, availability, maintainability, and safety. Maintainability even here is relevant because the question is, if we change something, how do we get it back into the process of the main open source project? So the ECSS tells us when we want to reuse software that hasn't been developed according to the ECSS, that we need to reenact the ECSS development process. We need to put ourselves in the same position we would have been had the software been developed according to the ECSS. So that means and reverse engineering, adding documentation, performing additional tests, and so on, as if it had been done according to the ECSS. And for us, we would estimate the cost of this to be in the area of 40 to 130 million euros based on cost points published for previous qualification projects, as far as they have been published. This is a linear extrapolation from smaller projects, so it's quite probable that the actual cost might even be larger than that, given that the complexity of both development and qualification tasks scale more than linearly with size. So this would be a cost less than re-implementation, but it's still not affordable. And so for us, the question would be, okay, if we cannot re-implement it, if we cannot qualify it, can we do the mission? If we say no, then the loss or the cost of this decision is the opportunity cost of the mission. It's the value of the mission itself. So instead, we propose a modified approach that tries to not simply reuse the software in question, but also not go the whole way towards those perhaps 130 million euros being spent. So in a first step, we would suggest to identify the functions and their criticality, as it is usually done for ECSS developments anyway. Then we would need to identify matching third-party software packages and map them to those functions, thereby these packages inheriting these criticality aspects. And then in the first step, we would try and find dependability evidence for these packages in order to minimize our later effort of qualification. So previous users of the software, the kind of process that is being used to develop the software, and so on, these are all admissible evidence for dependability here. And for everything that remains, we have quite a simple approach to adding dependability evidence on our own. Possible examples of dependability evidence could be, as I already mentioned, the development process and development infrastructure used in the development of the third-party software. So are there continuous integration setups, specified test requirements, reviews in proper order, and stuff like that? That would be something that we could count towards the dependability of that software. For example, ROS2 has quite a strict concept of reviews and maturity estimates for packages. Also, continuous integrations and automated tests with quite strict coverage requirements are present as well, which is much different from most other open source systems. Then we could look into successful use in same or other critical domains, such as aviation, automotive, or medicine. For example, here we could count towards ROS2 that it has been certified according to 26262, already at least parts of it. And then we would have to specifically consider the differences and the similarities between our application and the other applications. So if the open source software so far has only been used in simple information technology contexts without any criticality considerations regarding dependability or safety, then that would not be similar enough for us. Otherwise, if it has been used in a safety critical automotive application, that would count towards similarity. However, we need to be careful not to overlook critical differences between applications, otherwise we will be repeating Ariane 5. In order to guide evidence collection, we have identified a set of risk groups, and for each of these risk groups we have defined checklists. One of those risk groups could be the use of memory resources. And going through those checklists, we would first identify whether a risk is present. That means if anything fails in the software regarding this kind of risk, does this propagate to our complete system? If not, then we're done here. Otherwise, we can assess whether that risk might be acceptable. Maybe there's only minor consequences, and so we could accept that and don't have to do anything more. Otherwise, we might look into possible mitigations. For example, sandboxing parts of that software. If that is possible, we would apply that mitigation and, of course, also verify its proper implementation. Alternatively, we would now have to actually check the software for complete correctness, at least in those aspects that pertain to the specific risk group. If so, if it is possible to do that, we would apply the verification. And in both cases, we would later have to verify whether we were successful regarding reducing the risks to an acceptable level. One possible mitigation would be sandboxing, where we would put the non-compliant software into a sandbox together with some additional software that would check the results and maybe implement a localized fallback. If the problems that we have are in a small enough region, then this approach may still be less costly than re-implementing the non-compliant software, but we have to check for each individual case. So let's return to AI. What does the ECSS say about AI? Well, so far, nothing specific about handling the special challenges that come with AI. AI is being developed by example instead of refining requirements towards using proper logic. So it's a completely different approach to development than what we are used to so far, so we need a different approach. However, the question is, if it's so complicated, why even bother? Well, as I mentioned earlier, we might want an adaptive attitude controller here. And the question now is, how do you find or adapt the control parameters? One way would be to do it manually, but you see this sorry control engineer having to sit there for maybe weeks to finally tune the algorithm to the performance required. The other way around, it's already being done in so-called data-driven control design, where one aspect is, for example, system identification, which is being practiced for almost over 20 years now. The first user documents for applying system identifications are already older than 20 years. The main difference here is that in system identification, we try to identify the dynamics of the plant and then design the controller. In AI-based control, we simply skip that step and identify the controller that best controls our plant. So, considering that we don't know how AI reacts in all cases, how would we detect a failure? Well, one way could be to simply compare the actual motion of the system to the reference dynamics, which we should have specified in the first place in order to define what our behavior should be for which we have our controller. So we should have that control goal and simply compare the dynamics of the system to those reference dynamics. And if the deviation is large enough, we consider this as a failure. Another way that comes from AI is confidence measurement. We can train another AI to identify the difference between the current situation the system is in from the set of training situations that we have exposed the system to. And if the difference is large, that means that the controller might be less confident. And if this confidence goes beyond a specific cutoff level, we could switch back to a fallback. Also, we could use a voting approach where we have multiple independent AI-based controllers, and they are redundant and independent in their structure or training data. So they have a different structure or they have been exposed to different training data and thereby kind of represent independent experts on the same topics. And if these experts independently agree on a control output that would be close together, then we could accept that input. If they disagree, then we would need to fall back. And that fallback would probably be a classically trained algorithm, but it wouldn't be trained to the same performance. So we're saying we're going to save mode. In all of this, one topic comes up many times, and it's balancing risk and cost. We've seen that the cost of applying ROS2 in the usual way would be way too high, but also the cost of recreating it in the usual way would be way too high, so we wouldn't be able to do the mission. So the risk here is not doing the mission at all. So instead, we might think of ways of reducing the cost and accepting more risk. That is one option. The other option is, of course, to accept the higher cost and reduce the risk by that. However, we might also end up increasing the cost, but also increasing the risk. How can this be, you may ask? Well, looking at the formula for risk, which is essentially expected cost, in the most simple case, this is failure probability multiplied by the cost in case of failure. And this cost also includes our development cost. So if we increase the development cost by adding additional verification and validation activities, then we increase the cost, but we are not guaranteed to reduce the failure probability. So now risk may have increased, even though we have done additional V&V. And finally, the decisions about all of that are about sharing responsibility between the customer and the contractor. It's not a possible way to go for the customer to simply say, I want you to reduce the price by reducing V&V activities, but I also will hold you responsible financially if something fails later on. The risk and the savings must be shared on both sides. And that is possibly something that is not compatible with current contract designs. So that was just a quick glimpse over our work in this consortium. I thank you for your attention.